Right now, if you look toward the northern sky, specifically between the constellation Boötes and the familiar shape of the Big Dipper, you are staring into a region of space that contains almost nothing. Not a sparse scattering of stars. Not a thin field of distant galaxies. Genuinely, almost nothing. This region is called the Boötes Void, and it is the largest known cosmic void in the observable universe, spanning approximately 330 million light-years in diameter. To appreciate why that number is remarkable, consider this. The entire Milky Way galaxy, home to somewhere between 100 and 400 billion stars, stretches roughly 100,000 light-years across. The Boötes Void is more than 3,000 times wider than our entire galaxy. If you place the Milky Way inside the Boötes Void, it would be an almost imperceptibly small speck, like a single grain of sand dropped into the Grand Canyon. And yet, for a long time, nobody knew it was there. Not because scientists weren't looking, but because the void is, by definition, defined by what isn't there. It took a specific kind of survey, a deliberate effort to map what existed where in three-dimensional space, to reveal that this enormous region of the cosmos was conspicuously, unexpectedly empty. This video is about what the Boötes Void actually is, how it was found, what it tells us about the large-scale structure of the universe, and what would theoretically happen if you were somehow placed inside it. Along the way, we'll cover some of the most important and least discussed concepts in modern cosmology. The cosmic web, the role of gravity in shaping voids, and the strange fact that roughly 80% of the universe's volume is essentially empty space. Let's start with the discovery. Before we start, if you enjoy this content, please consider subscribing. Our goal is to reach 1,000 subscribers by the end of this month, so please show some support and help us get there. Now, let's get into the video. The discovery, mapping an invisible structure. The story of the Boötes Void begins in the late 1970s and early 1980s, during a period when astronomers were trying to do something genuinely ambitious: build the first three-dimensional map of the universe. Prior to this, most observations of the cosmos were essentially two-dimensional. Astronomers could measure where galaxies appeared in the sky, their angular position, but determining how far away they were was significantly harder. Distance in astronomy requires indirect measurements, and for very distant objects, the most reliable method available at the time was redshift. Here is how redshift works. When a source of light moves away from an observer, the wavelength of that light gets stretched. The light shifts toward the red end of the electromagnetic spectrum. The faster the object moves away, the greater the redshift. Because the universe is expanding, distant galaxies are moving away from us. The farther away a galaxy is, the faster it appears to recede, and therefore the greater its redshift. By measuring a galaxy's redshift, astronomers can calculate its recession velocity, and from that, estimate its distance. This relationship between redshift and distance is called Hubble's law, named after Edwin Hubble, who first established the observational evidence for cosmic expansion in 1929. By the 1970s, measuring redshifts had become a systematic observational practice, and astronomers began compiling large catalogues of galaxy redshifts with the explicit goal of producing a three-dimensional picture of how galaxies were distributed across space. This effort came to be known as redshift surveys. One of the key early efforts was led by astronomers Robert Kirshner, Augustus Oehmler, Paul Schechter, and Stephen Schechtman. In 1981, while analysing data from one such survey targeting a region of sky in the direction of the constellation Boötes, they noticed something that did not fit expectations. In a region of space covering a significant angular area of the sky and extending across a distance range corresponding to roughly 700 million light-years from Earth, they found almost no galaxies at all. Where their survey predicted finding hundreds of galaxies based on the average density of the universe at that scale, they found approximately 60. In a volume of space large enough to contain millions of Milky Way-sized galaxies, only about 60 actual galaxies showed up. The rest was empty. This was not a data error. The team carefully checked their methodology, verified their redshift measurements, and confirmed that the gap was real. They published their results in 1981, describing what they called a void in the galaxy distribution, a spherical, or approximately spherical, region of space with a diameter of around 300 million light-years that was essentially devoid of galaxies. The astronomical community took notice. Some were skeptical. The structure seemed too large. Given the prevailing models of how the universe was structured, a void of that size was difficult to explain, but subsequent surveys confirmed it. The Boötes Void was real, it was enormous, and it needed an explanation. How big is 330 million light-years, really? Before moving forward, it is worth spending some time making the scale of the Boötes Void genuinely comprehensible, or at least as close to comprehensible as the human mind can manage when dealing with these numbers. A light-year is the distance light travels in 1 year. Light moves at approximately 299,792 kilometers per second. In a single second, it covers a distance roughly equivalent to circling Earth 7.5 times. In 1 year, moving at that speed continuously, light travels approximately 9.46 trillion kilometers, or about 5.88 trillion miles. The nearest star to our Sun, Proxima Centauri, is about 4.24 light-years away. That means light leaving Proxima Centauri takes just over 4 years to reach us. The Milky Way galaxy, from one edge to the other, spans roughly 100,000 light-years. Light crossing the Milky Way from one side to the other would take 100,000 years. The Andromeda Galaxy, our nearest large galactic neighbour, sits approximately 2.5 million light-years away. That means when you look at Andromeda in the night sky, you are seeing light that left it 2.5 million years ago before anatomically modern humans existed on Earth. Now, the Boötes Void is 330 million light-years in diameter. That is 132 times the distance to the Andromeda Galaxy measured as a diameter. If you wanted to cross the void, travelling at the speed of light the fastest anything can travel, according to our current understanding of physics, it would take you 330 million years. To get from one edge to the centre would take 165 million years. For reference, 165 million years ago, Earth was in the middle of the Jurassic period. Dinosaurs were the dominant land vertebrates. The first birds were just beginning to evolve. Mammals existed, but were small, nocturnal, and largely marginal creatures. The Atlantic Ocean was just beginning to form as the supercontinent Pangaea continued to break apart. Modern humans, our entire genus, our entire primate lineage, did not yet exist. That is how long it would take to travel from one edge of the Boötes Void to its centre, even at the speed of light. In terms of volume, the Boötes Void contains approximately 236,000 cubic megaparsecs. A megaparsec is about 3.26 million light-years. The numbers quickly become abstract, but the practical implication is straightforward. This is the largest coherent empty structure ever measured in the observable universe, and it contains so little matter that even the galaxies that do exist inside it, approximately 60, by current estimates, would be invisible to the naked human eye from the center, the large-scale structure of the universe. To understand why the Boötes Void exists, you need to understand how the universe is structured on the largest scales. This is one of the most counterintuitive things about cosmology. When most people imagine the universe, they picture a roughly uniform distribution of stars and galaxies spread evenly through space, perhaps getting thinner towards some distant edge. That picture is wrong. The universe on its largest scales has a highly specific and deeply non-uniform structure. Matter is not spread evenly. It is organized into a vast, interlocking architecture that cosmologists call the cosmic web. The cosmic web consists of several types of structures. Filaments are long, thread-like chains of galaxies, and dark matter stretching across tens or hundreds of millions of light years. Sheets or walls are flat, planar arrangements of galaxies, forming the boundaries between large empty regions. Nodes, also called galaxy clusters or superclusters, are the densest concentrations of matter, located where filaments intersect. And voids are the large, roughly spherical regions of space that are enclosed by these filaments and walls, the bubbles in the foam. The overall appearance of this structure, when visualized, resembles foam or a sponge or a three-dimensional spiderweb. It is often described using the term cosmic foam or cosmic web. The matter in the universe is concentrated into thin, connected structures, and the spaces between those structures are the voids. This structure was not present at the very beginning of the universe. In the first few 100,000 years after the Big Bang, the universe was an almost perfectly uniform hot plasma. The density variations that existed were extraordinarily small, on the order of 1 part in 100,000. But those tiny variations mattered enormously over time. Regions that were even very slightly denser than average exerted a slightly stronger gravitational pull on surrounding matter. Over billions of years, that slight advantage compounded. Denser regions pulled in more matter from their surroundings, becoming even denser. This made the surrounding regions less dense, which reduced their gravitational pull, allowing even more matter to flow toward the denser concentrations. The rich got richer, the empty got emptier. This process, the gravitational collapse and accretion of matter into filaments, sheets, and nodes, is called gravitational instability, and it is the primary mechanism by which the large-scale structure of the universe formed. The cosmic web is the result of 13.8 billion years of gravity, acting on those initial tiny density fluctuations. The voids are the natural complement of this process. As matter flows toward filaments and superclusters, it drains out of the spaces between them. Voids are not anomalies or surprises. They are the expected consequence of how gravity shapes matter over cosmic timescales. Every void is effectively the negative space defined by the surrounding web of filaments. What makes the Boötes Void unusual is not that it exists, but that it is so large. At 330 million light-years across, it is significantly bigger than most voids observed in the universe. Typical cosmic voids range from about 30 to 100 million light-years in diameter. The Boötes Void is roughly 3 to 10 times larger than the typical range. This is what initially made astronomers uncertain about it, and what continues to make it an object of scientific interest today. Why is the Boötes Void so large? This is a question that does not yet have a fully settled answer, and it is one of the reasons the Boötes Void remains an active topic of research. Several hypotheses have been proposed over the decades since its discovery. The first and most straightforward is that the Boötes Void is simply the result of normal cosmic web formation. but represents a statistical outlier, a region where the initial density fluctuations happen to be slightly more uniform than average, meaning gravity had less to work with, fewer seeds to amplify into concentrations of matter. Over billions of years, this led to an unusually empty region. Under this explanation, the Boötes Void is rare but not impossible. Given the size of the observable universe, containing billions of galaxies and covering a diameter of about 93 billion light-years, you would expect some regions to be significantly emptier than average, simply by chance. The second hypothesis is that the Boötes Void might actually be a superposition of multiple smaller voids that overlap along our line of sight. If several separate void regions happen to be aligned, so that they appear as one continuous empty region from our perspective, the apparent size of the void would be larger than any individual void. Some research has suggested that this may account for at least part of the Boötes Void's unusual size, though the question is not fully resolved. A third line of inquiry involves the role of dark energy. The universe's expansion is accelerating, driven by dark energy, a poorly understood form of energy that appears to be distributed uniformly through space, and exerts a repulsive effect that counteracts gravity on the largest scales. In regions where matter density is already low, the effect of dark energy is more pronounced relative to gravity, meaning voids tend to expand. Dark energy effectively stretches voids wider over time. This could contribute to the Boötes Void being as large as it is today, even if it started somewhat smaller. A fourth, more speculative hypothesis, which has largely not gained traction in the scientific community, but is worth noting, is that the void could be the result of exotic physics, such as the remnant of a cosmic bubble nucleation event in the very early universe. This idea comes from certain theories of cosmic inflation and bubble cosmology, but there is currently no observational evidence supporting it specifically for the Boötes Void. The most likely explanation, based on current evidence and modelling, is a combination of the first and third factors. The Boötes Void formed through normal gravitational dynamics from favourable initial conditions and has been enlarged over time by the accelerating expansion of the universe driven by dark energy. But the full answer requires better observational data and more refined simulations of cosmic structure formation than currently exist. What is actually inside the Boötes Void? The name void implies absolute emptiness, and the Boötes Void is strikingly empty by cosmic standards, but it is not perfectly empty. Researchers have identified approximately 60 galaxies within its boundaries, a number that sounds substantial until you consider the scale involved. If those 60 galaxies were distributed uniformly throughout the void's volume, the average distance between any two of them would be tens of millions of light-years. For comparison, the Milky Way and the Andromeda galaxy are separated by about 2.5 million light-years, already a vast distance. The spacing between galaxies inside the Boötes Void would be many times larger than even that. In practice, those 60 galaxies are not uniformly distributed. They appear to be grouped into a single filament, a thread-like structure that runs through the interior of the void. This is actually consistent with the cosmic web picture. Even within a large void, the small amount of matter that remains tends to self-organize into structures under gravity, forming miniature versions of the filaments found in denser regions of the universe. The galaxies in this filament are small compared to typical galaxies in denser environments. This makes sense. In a void environment, there is less matter available to merge and build larger structures over time, so the galaxies that do form tend to remain smaller and less massive. Studies of void galaxies in general, not just in the Boötes Void specifically, have shown that they tend to be bluer, more diffuse, and have higher rates of star formation relative to galaxies in denser environments. This is thought to be because they have experienced fewer mergers and less tidal disruption, allowing their gas supply to remain more intact and available for star formation. Outside of those 60 galaxies, the rest of the Boötes Void contains gas, primarily hydrogen and helium, the same elements that dominate the overall composition of the universe, but at extraordinarily low densities. The intergalactic medium in a void is far more diffuse than even the most rarefied environments near galaxy clusters. This gas is also much colder than the hot X-ray emitting gas found in galaxy clusters, and it is largely invisible to direct observation without specialized instrumentation. There is also almost certainly dark matter inside the void, but less of it than in surrounding filaments and walls by definition. Dark matter does not clump as efficiently in low-density environments, and the void's interior represents a region where dark matter density is well below the cosmic average. The temperature inside the void. One of the more visceral ways to appreciate what the Boötes Void represents is to consider its temperature. The universe has a background temperature. This comes from the cosmic microwave background radiation. The afterglow of the Big Bang redshifted over 13.8 billion years into microwaves that now permeate all of space. The CMB has a temperature of approximately 2.725 Kelvin, or about negative 270.4 degrees Celsius, or negative 454.7 degrees Fahrenheit. That temperature applies essentially everywhere in the universe, including inside the Boötes Void. Kelvin is an absolute temperature scale. 0 Kelvin absolute zero is the theoretical minimum temperature, the point at which all thermal motion of particles ceases. There is no temperature lower than 0 Kelvin. The interior of the Boötes Void, at roughly 2.7 Kelvin, is barely above absolute zero. By comparison, room temperature is about 293 Kelvin. The surface of the Sun is about 5,778 Kelvin. The hottest regions near active galactic nuclei can reach billions of Kelvin. The interior of the Boötes Void sits at 2.7 Kelvin, a temperature so cold that it is almost indistinguishable from the theoretical minimum. There is no source of heat inside the void to raise this temperature. In a region with galaxies and stars nearby, radiation from those sources contributes to local heating of the intergalactic medium. Inside a large void, those heat sources are absent or extremely distant, leaving the interior as one of the coldest environments in the known universe. What it would be like to be inside the Boötes Void. This is a thought experiment, not a practical possibility. The physics of travelling to the Boötes Void, let alone surviving there, involve obstacles that are either currently impossible or would require technology so far beyond our current capabilities that the gap is essentially unbridgeable. But thought experiments are useful. They make abstract physical concepts concrete, and they reveal aspects of reality that are otherwise easy to overlook. So, what would it actually be like to be inside the Boötes Void? The first thing to understand is that getting there at all would be an extraordinary undertaking. The Boötes Void is approximately 700 million light-years from Earth. The fastest human-made object ever launched is the Parker Solar Probe, which reached a peak speed of approximately 163 kilometers per second during a close solar flyby. That is fast by any terrestrial standard, fast enough to cross the continental United States in about 25 seconds. But as a fraction of the speed of light, it is 0.054%. At that speed, reaching the Boötes Void would take approximately 1.3 trillion years. For reference, the current age of the universe is about 13.8 billion years. Travelling to the Boötes Void at our fastest current speed would take roughly 94 times the current age of the universe. Even at the speed of light, the absolute upper limit set by special relativity, a limit that applies to any object with mass and therefore cannot actually be reached, the journey would take 700 million years. That is comparable to the entire span of complex animal life on Earth, from the earliest multicellular animals of the Ediacaran period, through every subsequent evolutionary transition up to the present day. So, for the purposes of this thought experiment, assume a spacecraft capable of travelling at or near the speed of light, with full life support systems, and with some mechanism of shielding occupants from the consequences of relativistic travel. None of this is currently achievable. All of it is assumed for the sake of exploring what the void itself would be like, the journey toward the void. Leaving Earth and the solar system is itself a multi-step process that is easy to underestimate. Earth orbits the Sun at an average distance of about 150 million kilometers, moving at roughly 30 kilometers per second. To leave the solar system, a spacecraft cannot simply accelerate outward in a straight line. It must first escape Earth's gravitational influence, then work against the Sun's gravity, which extends, in a meaningful sense, well beyond the orbit of Neptune. The boundary of the Sun's gravitational dominance, the region where the solar wind gives way to interstellar space, is called the heliopause, and it lies roughly 120 astronomical units from the Sunday. 1 astronomical unit is the average Earth-Sun distance. The heliopause sits about 18 billion kilometers away. Voyager 1, launched in 1977, crossed the heliopause in 2012, making it the first human-made object to enter interstellar space. It took 35 years to cover that distance. In the context of a journey to the Boötes Void, crossing the heliopause is barely a first step. It represents an infinitesimally small fraction of the total distance. Once beyond the heliopause, the spacecraft would enter the interstellar medium of the Milky Way. Here, stars are separated by light years, but they are still present. The night sky, or whatever direction the spacecraft was not pointed, would remain full of stars. The Milky Way's disk, seen from inside, forms the familiar band of light visible from dark sites on Earth. This stellar environment persists for a long time. The Milky Way's disk is roughly 100,000 light-years in diameter, and Earth sits about 26,000 light-years from the galactic center. Reaching the outer edge of the Milky Way's disk, traveling directly outward from Earth's position, would take roughly 26,000 years at the speed of light. Beyond the disk, the stellar density drops off dramatically. The halo of the Milky Way contains globular clusters and some older stars, but the environment becomes noticeably less populated. Eventually, the spacecraft would pass beyond even these sparse outer regions and enter the intergalactic void between the Milky Way and other galaxies. At this point, after tens of thousands of years of light-speed travel, the stars would be mostly behind the spacecraft. Looking back, the Milky Way would appear as a flat, luminous disk. Looking forward, the sky would begin to darken. Distant galaxies would be visible as faint smudges of light. The nearest large ones, still millions of light-years away, but the immediate environment would be growing emptier. The spacecraft would pass through the local group, the collection of galaxies gravitationally bound to the Milky Way, including Andromeda, the 2 Magellanic Clouds, and several dozen smaller dwarf galaxies. The local group spans roughly 10 million light-years. Beyond it lies the Virgo supercluster, a larger structure containing hundreds of galaxy groups and clusters, of which the local group is just one small member. Beyond the Virgo supercluster, the spacecraft would enter the broader cosmic web. Filaments of galaxy clusters would periodically appear concentrations of light in certain directions, and the spaces between them would grow more pronounced. The sky would begin to look patchy, clusters of galaxies in some directions, growing emptiness in others. After hundreds of millions of years of travel, the spacecraft would approach the boundary of the Boötes Void. From the outside, there would be no dramatic demarcation, no wall, no transition zone with a clear edge. The galaxy density would simply decline gradually. Filaments and galaxy clusters would become visible only in certain directions. The surrounding cosmic web still present, but increasingly off to the sides as the spacecraft headed into the interior. Then, slowly, even those would begin to fade, crossing into the void. The transition into the Boötes Void would not feel like crossing a boundary. It would feel like gradual disappearance. At the outer edge of the void, some galaxies would still be visible in most directions, faint, distant, but present. As the spacecraft moved inward, they would recede. The galaxies behind the spacecraft in the direction of the cosmic web would grow fainter as the distance increased. The galaxies ahead deeper into the void were already absent. The sky would begin to dim in more and more directions. The speed of light places a hard limit on what can be seen. A galaxy 100 million light-years away is visible only because light that left it 100 million years ago is reaching us now. As the spacecraft moves deeper into the void, the nearest galaxies are getting farther away, their light arriving fainter and more redshifted. By the time the spacecraft reached a point several tens of millions of light-years inside the boundary of the Boötes Void, the sky would be dramatically darker than anything a human had ever experienced. Not the darkness of a clear night on Earth, where thousands of stars are visible and the Milky Way forms a bright band overhead. Not the darkness of interstellar space, where the Milky Way and nearby galaxies still provide substantial illumination. This would be a fundamentally different kind of dark. The human eye can detect galaxies down to approximately magnitude 6, the same limit that applies to faint stars visible from dark sites. A galaxy, like the Andromeda Galaxy, at 2.5 million light-years, has an apparent magnitude of about 3.4, making it visible to the naked eye under good conditions. But magnitude decreases, meaning objects become dimmer with the square of distance. A galaxy like Andromeda, moved to a distance of 100 million light-years, would have an apparent magnitude far below the threshold of naked eye visibility. From the center of the Boötes Void, the nearest galaxy is approximately 10 million light-years away, nearly 4 times the distance to Andromeda from Earth. A galaxy comparable in brightness to Andromeda at that distance would be just barely at or below the threshold of naked eye detection, and that is the nearest galaxy. The rest are farther still. In practical terms, from the center of the Boötes Void, a human observer without optical instruments would see nothing. No stars, because there are no stars nearby. No galaxies, because even the nearest ones are too far away and too faint for the unaided eye. The sky in every direction would appear completely black. This is a qualitatively different experience from any darkness humans have encountered or can easily imagine. In a dark cave, blocking all light sources, there is still the knowledge that light exists, that a few steps would bring you to an entrance, that the sun is above the rock. In a sensory deprivation tank, the water provides tactile feedback. In interstellar space, within a galaxy, the Milky Way's glow provides a continuous reference. In the Boötes Void, at its center, there would be no reference point at all, no direction that was brighter than another, no gradient of light providing any sense of orientation, gravity, and motion in the void. The physical experience of being in the Boötes Void would also differ in a subtle but profound way from being near a massive object. In deep space near a galaxy or star, there are gravitational gradients, The pull of nearby massive objects creates a preferred direction, however slight. Even in orbit around Earth, where astronauts experience weightlessness, there is a clear reference: the planet below, the direction of orbital velocity, the direction of the Sunday. In the Boötes Void, the nearest significant concentrations of mass are tens of millions of light years away. Gravity falls off with the square of distance. At those distances, the gravitational influence of even a large galaxy cluster would be extraordinarily weak, not zero, but far below any threshold of detectability with normal instruments, and completely imperceptible to a human body. The result would be genuine, uncommitted microgravity. Not the simulated weightlessness of Earth orbit, where you are technically in freefall around a planet. Not the reduced gravity of deep interplanetary space, where the sun's pull still provides a weak reference. In the Boötes Void, you would float in a truly isotropic gravitational field, or the closest thing to one that exists in the real universe. Every direction would be, in a gravitational sense, equivalent. There would be no preferred down, no preferred direction of motion. If you were floating outside a spacecraft and you let go of it, you would remain approximately stationary relative to the spacecraft. There would be no local gravitational gradient to cause relative drift. The spacecraft and its occupant would drift together through the void, carried by whatever velocity they had when they entered it, gradually slowing relative to the cosmic web due to the Hubble flow, the expansion of space itself. This would make navigation uniquely difficult. On Earth, we use landmarks and GPS. In the solar system, spacecraft navigate using the positions of the Sun and planets. In the Milky Way, the positions of known stars and radio sources provide reference. In the Boötes Void, the reference points the surrounding galaxies would be too faint to see with the naked eye, and would be millions of light years distant even with instruments. Determining your position within the void would require extremely sensitive instruments capable of detecting the faint light of very distant galaxies, correlating those signals with known maps of the void's surroundings. If your instruments failed and your spacecraft's internal navigation system lost its reference, orienting yourself would be genuinely impossible. You would have no way of knowing which direction led back toward the edge of the void, and which led deeper into it. You would be, in the most literal possible sense, lost. The cosmic microwave background in the void. One thing that would not change significantly inside the Boötes Void is the cosmic microwave background radiation. The CMB is not light coming from a specific direction. It is a background radiation field that permeates all of space, coming equally from all directions. It is the redshifted remnant of the hot plasma that filled the universe before atoms formed, approximately 380,000 years after the Big Bang. Today, 13.8 billion years later, that radiation has been stretched by cosmic expansion to wavelengths in the microwave range, corresponding to a temperature of 2.725 Kelvin. Inside the Boötes Void, the CMB would be present at the same intensity and temperature as anywhere else in the observable universe. It would be the primary source of ambient radiation, not from galaxies or stars, which are absent, but from this omnidirectional background field that fills all of space uniformly. A spacesuit or spacecraft in the Boötes Void would be bathed in this 2.725 Kelvin microwave radiation from all directions simultaneously. Without additional heat sources, a spacecraft would eventually equilibrate to that temperature, an extraordinarily cold state that would require significant active thermal management to prevent the spacecraft and its occupants from cooling to dangerous temperatures. The CMB also provides, in principle, a reference frame. The CMB appears very slightly hotter in the direction your spacecraft is moving toward, and slightly cooler in the direction you're moving away from a Doppler-like effect called the CMB dipole anisotropy. By measuring this dipole, a sufficiently sensitive spacecraft could determine its direction and speed of motion relative to the CMB rest frame. This would provide a form of navigation even without local reference points, but it requires extremely precise measurements of microwave radiation temperature differences on the order of millikelvin. The existence of the CMB in the void also has an interesting implication for the question of what the void looks like from the perspective of electromagnetic radiation. A radio telescope sensitive to microwave frequencies pointed in any direction from the center of the Boötes Void would see the CMB and very little else. The 60 galaxies inside the void would be detectable at radio wavelengths if they contain radio-emitting sources, but they would be sparse and faint. The dominant electromagnetic signal in the void at microwave frequencies would be the CMB itself. Void galaxies. Surviving in emptiness. The approximately 60 galaxies confirmed to exist within the Boötes Void represent an interesting special case in galaxy evolution. How do galaxies form and evolve in an environment that is so drastically underdense compared to the cosmic average? Galaxy formation in general depends on the availability of gas, primarily hydrogen, and on gravitational conditions that allow that gas to cool and collapse into star-forming clouds. In dense environments, like galaxy clusters, galaxies experience frequent interactions, mergers, tidal stripping, ram pressure from the hot intracluster gas. These interactions can both trigger star formation and shut it down. The environment shapes the galaxy. In a void environment, the situation is almost the reverse. There are very few neighboring galaxies to interact with. The intergalactic medium is cold and diffuse rather than hot and dense. Galaxies in voids are gravitational islands, isolated systems evolving largely on their own internal dynamics. Studies of void galaxies across various cosmic voids, not just the Boötes Void specifically, but void environments in general, have identified some consistent characteristics. Void galaxies tend to be less massive than typical galaxies in denser environments. They tend to be bluer in color, meaning their stellar populations are dominated by younger, hotter stars. They show higher rates of star formation per unit of stellar mass, what astronomers call specific star formation rate. And they tend to be more disk-like, with fewer of the elliptical galaxies that dominate cluster environments. These properties make sense in the context of void evolution. Without frequent mergers, galaxies retain their disk structures rather than being disrupted into ellipticals. Without ram pressure stripping from a hot intracluster medium, they retain their gas supply. With that gas supply intact, they continue to form new stars. The result is a galaxy that is still actively growing, still blue, and star-forming, while galaxies in dense environments have often exhausted their gas through mergers and environmental interactions. The galaxies inside the Boötes Void, if they follow this pattern, would represent relatively pristine, undisturbed systems galaxies that have evolved in near isolation for billions of years, unaffected by the complex gravitational and hydrodynamic interactions that shape galaxies in the cosmic web. From inside the void, if you could somehow navigate to one of those 60 galaxies, you would arrive at an ordinary-looking galaxy, probably a blue spiral, still forming stars, probably smaller than the Milky Way. Looking out from within such a galaxy, you would see the void in all its emptiness. The surrounding cosmic web would be visible distant filaments of galaxy clusters on the void's far side, but the vast majority of the sky in most directions would be empty. Even from within one of those 60 galaxies, the nearest other galaxy in the void would be tens of millions of light years away. The void is so large and contains so few galaxies that even the galaxies inside it are largely isolated from each other. Voids and the fate of the universe. The Boötes Void is not static. Like all structures in the universe, it is evolving, and the direction of that evolution is toward greater emptiness. The universe's expansion is accelerating. Dark energy, whatever it actually is, at a fundamental level, is causing space itself to expand at an increasing rate. This expansion affects structures at different scales in different ways. At small scales within galaxies, within galaxy clusters, within the local group gravity, is strong enough to hold structures together against the expansion. The Milky Way and Andromeda will merge in several billion years, not because of cosmic expansion, but because local gravity dominates. The local group is gravitationally bound. At the scales of the cosmic web superclusters, filaments, and voids, the situation is different. Gravity is still the dominant force in the dense structures, but in the voids, where matter density is far below average, dark energy's influence is more pronounced. The void expands. The matter inside it, primarily gas and dark matter, plus those 60 galaxies, is slowly pulled toward the void's boundaries by the gravity of the surrounding cosmic web. Over billions of years, voids tend to grow larger and emptier as matter drains out of them into the surrounding filaments and walls. The Boötes Void, in this picture, is not at its maximum size. It is still growing. Over cosmological timescales, tens of billions of years, it will expand further. The few galaxies inside it will migrate toward its edges, and the interior will become even more barren. On even longer timescales, hundreds of billions to trillions of years, the accelerating expansion of the universe will begin to affect even the gravitationally bound structures. The local group will eventually become isolated from all other galaxy groups as the expansion carries everything else beyond the cosmic horizon. Individual galaxies will stop forming stars as their gas runs out. Stars will age and die. Eventually, on timescales of 10, 14 years and beyond, even stellar remnants will fade, and the universe will approach a cold, dark, diffuse state. The Boötes Void represents a preview of a possible far future, a universe that is mostly empty space, with only isolated islands of matter separated by incomprehensible distances. Studying the void now, at this stage of cosmic history, gives cosmologists a window into both the past, how the cosmic web formed, and the future, where the universe might be heading. The physics of voids. What they tell us about the universe. Cosmic voids are not merely interesting for their scale or their emptiness. They are scientifically valuable in ways that are distinct from what galaxy clusters and filaments can tell us. In fact, the study of voids has become one of the more productive areas of observational cosmology over the past 2 decades, precisely because the physics that governs voids is simpler and in some ways more transparent than the physics of dense environments. Here is why that matters. In dense environments, galaxy clusters, for example gravity, gas dynamics, magnetic fields, radiation pressure, and dark matter, all interact in complex, non-linear ways. Understanding what is happening in a cluster requires disentangling these multiple overlapping effects. The physics is rich but messy. Building accurate models requires sophisticated simulations and many free parameters. Voids are different. In a void, the matter density is far below the cosmic average. Gravitational interactions between structures are weaker. Gas dynamics are simpler. The dominant influence on the evolution of a void is the combination of gravity pulling matter toward the surrounding dense regions and dark energy driving the expansion of the void itself. Because voids are underdense, their evolution is closer to linear, meaning the mathematical approximations that physicists used to describe early universe perturbation theory apply for much longer in voids than in dense regions. Voids remain in a regime that is more analytically tractable. This makes voids useful as a diagnostic tool for cosmological parameters. Specifically, voids are sensitive probes of dark energy. Voids as dark energy detectors. Dark energy is one of the central, unsolved problems in modern physics. Observations of type Ia supernovae in the late 1990s established that the expansion of the universe is accelerating, a result recognized with the 2011 Nobel Prize in Physics. The most straightforward explanation for that acceleration is a cosmological constant, a fixed energy density associated with empty space, represented by the Greek letter lambda in Einstein's field equations. This is often called vacuum energy. The cosmological constant model fits current observations well, but it raises a profound theoretical problem. Quantum field theory predicts that the vacuum energy of empty space should be enormous, many orders of magnitude larger than the value inferred from cosmological observations. The discrepancy between the theoretically predicted and observationally measured values of vacuum energy is one of the largest unsolved problems in physics. Alternative models of dark energy propose that it is not a fixed constant, but a dynamic field that varies over space and time. These models are collectively called quintessence models, and they make predictions about how the expansion rate of the universe changes over cosmic history that differ subtly from the simple cosmological constant model. Distinguishing between a cosmological constant and dynamic dark energy requires very precise measurements of how cosmic expansion has evolved over time and space. This is where voids come in. The size distribution of voids, how many voids of each size exist at each cosmic epoch, is sensitive to the expansion history of the universe. If dark energy is a cosmological constant, voids of different sizes should exist in specific predicted ratios. If dark energy is a dynamic field, those ratios would be different. By measuring the size distribution of voids at different redshifts and different look-back times, cosmologists can in principle constrain dark energy models independently of supernova measurements. Voids also provide a test through a phenomenon called the integrated Sachs-Wolf effect. This is a subtle imprint on the cosmic microwave background caused by photons traveling through regions of space where the gravitational potential is changing. As a CMB photon enters a large underdense region like a void, it gains a small amount of energy climbing out of a potential well. As the void grows driven by dark energy, the photon leaves through a shallower potential than it entered, gaining a net energy boost. The result is a slight temperature increment in the CMB, in the direction of large voids. Detecting this signal requires correlating CMB temperature maps with maps of the large-scale structure specifically, identifying where voids are and checking whether the CMB is slightly warmer in those directions. This has been observed, and the signal is consistent with the presence of dark energy. Future surveys with higher sensitivity will be able to use this signal to place much tighter constraints on dark energy's properties. The Boötes Void, as the largest known void, would in principle produce one of the largest such signals. But its distance, 700 million light-years, means that the signal is small and hard to disentangle from noise. Larger, more nearby voids actually provide cleaner signals for this particular measurement. The cosmic web in detail, filaments, walls, and superclusters. To fully appreciate the Boötes Void, It helps to understand the specific structures that surround and define it, the filaments and walls that form its boundaries. The Boötes Void is bounded on various sides by galaxy filaments and walls. Among the most prominent neighbouring structures is the CFA 2 Great Wall, also called the Coma Wall, a sheet-like arrangement of galaxies discovered in 1989 by Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics. The Great Wall, as it was then called, stretches approximately 500 million light-years in length and 300 million light-years in width, making it one of the largest known structures in the universe at the time of its discovery. Subsequently, even larger structures have been found. The Sloan Great Wall, identified in 2003 using data from the Sloan Digital Sky Survey, stretches roughly 1.37 billion light-years. The Hercules Corona Borealis Great Wall, proposed in 2013 and refined in subsequent studies, may extend up to 10 billion light-years, though its status as a coherent, gravitationally bound structure is debated. At scales larger than about 300 million light-years, the universe is expected to become homogeneous and isotropic meaning structures. Larger than this would violate the cosmological principle, the foundational assumption that the universe looks the same in all directions on large enough scales. The Boötes Void sits within this broader cosmic architecture. It is one node of emptiness within the cosmic foam, surrounded by walls and filaments that carry the material that the void has, over billions of years, expelled. Understanding the three-dimensional geometry of this structure, where exactly the filaments are, how they connect to other structures, how the Boötes Void relates geometrically to other nearby voids, requires detailed redshift surveys covering large areas of the sky with high completeness. Early surveys in the 1980s were limited by the relatively small number of galaxy redshifts that could be measured by hand. Modern surveys have transformed this picture dramatically. Modern surveys and the Boötes Void. The discovery of the Boötes Void in 1981 was made using data from a relatively modest survey, a few hundred galaxy spectra in a targeted region of sky. Since then, the technology and scale of galaxy surveys has advanced enormously. The Sloan Digital Sky Survey, which began operations in 2000 and has continued through multiple phases, has measured spectra and redshifts for hundreds of millions of galaxies and quasars. It covers roughly a third of the entire sky and has produced the most detailed three-dimensional map of the local universe ever assembled. Within this map, the large-scale structure, the filaments, walls, clusters, and voids of the cosmic web is visible with extraordinary clarity. The 2DF Galaxy Redshift Survey, conducted using the Anglo-Australian telescope, measured over 200,000 galaxy redshifts in the late 1990s and early 2000s and produced complementary mapping of the southern sky. More recently, the Dark Energy Spectroscopic Instrument, known as DESI, has begun the most ambitious galaxy survey yet undertaken, targeting 40 million galaxies and quasars over a 5-year observing period. DESI's primary scientific goal is constraining dark energy by measuring the baryon acoustic oscillation scale, a standard ruler imprinted in the distribution of galaxies that allows precise measurements of the universe's expansion history. But it will also produce an unprecedentedly detailed map of the cosmic web, including voids, at higher redshifts than previous surveys. The Euclid mission, launched by the European Space Agency in July 2023, is a space-based survey telescope designed to map the geometry of the dark universe over a large fraction of the sky and out to significant cosmological distances. It will also produce detailed void catalogues and contribute to constraints on dark energy and the growth of large-scale structure. These surveys are transforming void science from a niche observational curiosity into a precision cosmological tool. The Boötes Void, as the largest known void, remains a reference point in this broader enterprise, a landmark in the cosmic web that helps calibrate our understanding of structure formation on the largest scales, the cosmological principle, and the challenge of large structures. The existence of the Boötes Void and of other very large structures in the cosmic web raises a genuine scientific tension that is worth discussing carefully. Modern cosmology rests on the cosmological principle, the assumption that the universe, on large enough scales, is homogeneous and isotropic. Homogeneous means the same in every place. Isotropic means the same in every direction. The cosmological principle does not say the universe is perfectly uniform on small scales. Clearly, it is not, given that galaxies, clusters, and voids exist. It says that when you average over large enough volumes, the universe looks the same everywhere. The scale at which the universe is expected to become homogeneous is approximately 300 to 400 million light years. Below this scale, structures like voids, filaments, and superclusters are expected and predicted by models. Above this scale, the density of the universe should converge to a smooth average. The Boötes Void, at 330 million light-years, sits right at this boundary. Its size is at the upper limit of what standard cosmological models predict should be possible for a void. It is not necessarily in violation of the cosmological principle, but it is large enough to be uncomfortable, large enough that its existence was initially met with skepticism and continues to motivate careful analysis. The concern is this: if the Boötes Void is genuinely a single coherent void at 330 million light-years, and if other comparably large structures exist elsewhere in the universe, then the scale of homogeneity might be larger than standard models predict. This could indicate that the cosmological principle needs revision, or that something about our models of structure formation is missing. The superposition hypothesis, the idea that the apparent Boötes void might be several smaller, overlapping voids along the line of sight, partially resolves this tension. If the void is actually composed of multiple structures at slightly different distances that happen to align, the individual component voids would be within the expected size range. However, demonstrating this conclusively requires precise three-dimensional mapping of the void's interior, which is difficult given its distance and the faintness of the galaxies within it. This is an active area of research. Better surveys and improved analysis techniques are gradually building a more complete picture. The current consensus is that the Boötes Void is a real underdensity. The region is genuinely emptier than average, but its exact geometry, whether it is a single void or a composite structure, remains somewhat uncertain. What scientists still don't know. Despite decades of study since its discovery in 1981, several important questions about the Boötes Void remain unresolved. The first is its precise internal structure. The current catalogue of roughly 60 galaxies within the void is based on surveys that were not specifically designed to achieve high completeness within this region. It is possible that there are more galaxies inside the Boötes Void fainter, smaller, or otherwise harder to detect that have not yet been identified. A dedicated, deep survey of the void's interior, using modern instrumentation capable of detecting very faint galaxies, would significantly improve our understanding of what is actually inside it. The second open question concerns the void's exact geometry and boundaries. The Boötes Void is not a perfect sphere. It has an irregular shape, and its boundaries where the void transitions into the surrounding cosmic web are not sharply defined. Mapping this boundary region in 3 dimensions, determining exactly where the void ends and the surrounding filaments begin, requires comprehensive redshift measurements of the galaxies in the transition zone. This is technically feasible with current technology, but has not yet been done systematically. The third question is the formation history of the void. Standard cosmological models, particularly the lambda CDM model, the current consensus model of cosmology, incorporating cold dark matter and a cosmological constant, can produce voids of various sizes through simulations. Whether these simulations specifically reproduce a void as large as the Boötes Void with the correct frequency, whether it is a 1 in a billion outlier, or something more common, has implications for whether the standard model is complete. Comparing the observed size distribution of the largest voids with the predictions of cosmological simulations is an ongoing effort. The fourth question is the nature of the dark matter and dark energy environment inside the void. Dark matter does not emit light and cannot be observed directly. Its distribution inside the Boötes Void can only be inferred through its gravitational effects, primarily through weak gravitational lensing. The subtle distortion of background galaxy shapes by intervening mass. Measuring weak lensing through and around the Boötes Void would provide a map of the dark matter distribution in this region. This is technically challenging at the void's distance, but may become feasible with next-generation surveys. The fifth question is more fundamental. Does the Boötes Void represent a problem for the cosmological principle? This question will only be resolved through comprehensive surveys that map the universe's structure with sufficient completeness to determine whether structures as large as the Boötes Void are statistically consistent with standard models or represent genuine anomalies. The broader significance of voids. The Boötes Void is the most extreme known example of a class of structures, cosmic voids, that collectively make up roughly 80% of the volume of the observable universe. That statistic deserves reflection. If you were to choose a random point in the observable universe, there is approximately an 80% chance that point would lie inside a void, a region where the matter density is well below the cosmic average. The filaments, walls, and clusters that contain the vast majority of the universe's galaxies and stars occupy only about 20% of the universe's volume, despite containing most of its visible matter. This inversion, where the structures containing most of the matter occupy a minority of the volume, is a direct consequence of the physics of gravitational collapse. Matter concentrates. It flows from underdense regions into overdense ones, compressing into thin sheets and filaments rather than distributing itself uniformly. The cosmic web is geometrically dominated by emptiness, with matter threaded through it in relatively thin structures. Understanding voids is therefore understanding the majority of the universe by volume. Voids are not exotic exceptions to the normal state of the cosmos. They are the normal state in terms of how most of space is actually configured. This perspective shifts the framing of the question. Rather than asking why such a large void exists, it is worth recognizing that voids are the default and the cosmic web's dense structures are the exception, the result of matter having been actively pulled out of vast regions by gravity over billions of years. The Boötes Void, as the largest known example, represents this default state in its most extreme form. It is the universe in its most undisturbed configuration, a region where matter has been most thoroughly evacuated, where the cosmic web's influence is most distant, and where the underlying geometry of space can be studied with minimal contamination from the complex astrophysics of dense environments. The future of Boötes Void research. The next decade will likely produce significantly improved understanding of the Boötes Void and of cosmic voids more broadly. The DESI survey, currently underway, will measure galaxy redshifts with high completeness across large areas of the northern sky, including the region containing the Boötes Void. Its data will allow a much more detailed, three-dimensional reconstruction of the void's interior and boundaries than has previously been possible. By identifying more of the galaxies within the void, both the dominant filament of roughly 60 known galaxies and any additional fainter galaxies not yet catalogued, DESI data will constrain the void's true internal structure. The Vera C. Rubin Observatory, scheduled to begin full survey operations in 2025 and now in early commissioning phases, will conduct the Legacy Survey of Space and Time, a 10-year imaging survey of the southern sky reaching extraordinary depth. While the Boötes Void is primarily in the northern sky, and therefore not Rubin's primary target, its sensitivity to very faint objects will improve the general methodology of void galaxy detection and characterization. The Euclid mission will provide weak gravitational lensing maps covering a large fraction of the sky, enabling the first detailed mapping of the dark matter distribution in and around large voids. Applied to the region containing the Boötes Void, this could provide the first observational constraints on the dark matter density profile of the void itself. Improved cosmological simulations run on next-generation supercomputers with higher resolution and larger simulation volumes will allow more direct comparison between the observed properties of the Boötes Void and the predictions of standard cosmological models. These comparisons will test whether the void's size and internal structure are consistent with lambda CDM, or whether they require modifications to the model. Radio surveys may also contribute. Low-frequency radio observatories, like the Square Kilometre Array, under construction in South Africa and Australia, will detect radio emission from galaxies across enormous volumes of space. Their sensitivity to faint, low-surface brightness sources may reveal previously unknown galaxies within the Boötes Void, improving the completeness of the Void galaxy catalogue. Taken together, these observational and theoretical advances will transform our understanding of the Boötes Void from a landmark discovery, a surprisingly large region of emptiness found in an early redshift survey, into a precision cosmological laboratory, a region of the universe where the physics of dark energy, large-scale structure formation, and galaxy evolution in extreme environments can all be studied in detail. Putting it all together, the Boötes Void was discovered because astronomers were trying to map where things are in the universe, and they found a place where almost nothing is. At 330 million light-years across, it is the largest known coherent underdensity in the observable universe. It lies 700 million light-years from Earth, in the direction of the constellation Boötes, and can, in principle, be located by anyone who knows where to look between the Big Dipper and the bright star Arcturus. Inside it, the temperature is approximately 2.7 Kelvin, barely above absolute zero. The nearest galaxy to any point at its centre is tens of millions of light-years away. Approximately 60 galaxies have been identified within its volume, organised into a single filament threading through the interior. To the naked eye, from the centre of the void, the sky would be completely black in every direction. The void exists because gravity shaped the universe from tiny initial density fluctuations into the cosmic web, a structure of filaments, walls, clusters, and the voids between them. The Boötes Void is an especially large bubble in this foam, a region where the initial conditions were favourable for producing an unusually empty space, enlarged over time by the accelerating cosmic expansion driven by dark energy. It is not in violation of our current models, but it sits at their edge large enough that its precise nature, whether a single void or a superposition of several, remains an active scientific question. Studying it has practical scientific value. Voids in general, and large voids like the Boötes Void in particular, are sensitive probes of dark energy and of the expansion history of the universe. They represent the simplest large-scale environments in the cosmos regions, where the complex physics of dense environments is absent and the underlying cosmological dynamics can be studied more clearly. They are also, in a very real sense, the dominant feature of the universe when measured by volume. The cosmic web is mostly empty space. The Boötes Void is the largest example of that emptiness that we have yet found. Whether a larger void exists somewhere in the observable universe in a region not yet mapped by our surveys is an open question. The observable universe spans about 93 billion light-years in diameter. Our surveys, even the most comprehensive, have not yet mapped it uniformly to the depth required to find every large structure. The Boötes Void was found because astronomers looked in the right direction with the right instrument at the right time. Other structures, potentially even larger, may be waiting in regions not yet surveyed with sufficient depth. For now, the Boötes Void stands as the largest known void, a 330 million light-year region of near-total emptiness, embedded in a universe where such emptiness is, in fact, the rule rather than the exception.